Hello viewers, in today's session we are going to discuss another important problem from definite integrals, and in this session we are going to solve this problem in which the fundamental theorem of integral calculus is used, right? So let us first read out this problem and then we'll see how easily we can solve this problem with the help of fundamental theorem of integral calculus, right? So here we are given a function f from R to R, where R is the set of real numbers, and here we are given an equation that is x plus 2 times the integral 0 to x f of t dt is equal to e raised to 2x minus pi, right? For all x belonging to the set of real numbers. Then we have to find all the values of x, or the range of x for which the function f of x, it satisfies this inequality, right? That is, f of x is greater than or equal to 2 but less than or equal to 5, right? So let us start. So here we are given this equation that is x plus 2 times the integral 0 to x f of t dt is equal to e raised to 2x minus pi, right? Now see, here we have this integral that is from 0 to x f of t dt. Now see, the fundamental theorem of integral calculus says that if we have a function, say a of x, that is equal to 0 to x f of t dt, then the derivative of this function a of x, that is a prime of x, is equal to d by dx of the integral 0 to x f of t dt is equal to simply f of x, right? So a prime of x is equal to f of x. So here we are going to use this result. So let us differentiate both sides of equation 1 with respect to x. So now we can write d by dx of x. The first term is x, and then we have 2 times the derivative of the integral 0 to x f of t dt, and here we have d by dx of e raised to 2x minus pi, right? Now the derivative of x with respect to x is 1, and here we have 2 times. Now using this result, see, the derivative of 0 to x f of t dt is equal to f of x. So here we have 2 times f of x, and here the derivative of e raised to 2x is 2 times e raised to 2x, and the derivative of pi is 0, being a constant. So now we have this equation. So we can now write 2 times f of x is equal to 2 times e raised to 2x minus 1. So this is our equation 3. So now here we are given this inequality, that is f of x satisfies this inequality. So here we have 2 less than or equal to f of x, and this is further less than or equal to 5. Now let us multiply this inequality throughout by 2, because here we have 2 times f of x. So here we have 4, and here we have 2 times f of x, and this is 2 times 5 is 10. Now we can substitute the value of 2 times of f of x as 2 times e raised to 2x minus 1. So we have 4, and here we have 2 e raised to 2x minus 1, and here we have 10, right? Now we have to solve this inequality to get the values of x, or the interval in which x belongs to when f of x lies between 2 and 5. So now let us add 1 throughout. So here we have 4 plus 1, and here we have 2 times e raised to 2x. Here 1 and minus 1 and plus 1 get cancelled, and here we have 10 plus 1. So we have 5, and here 2 times e raised to 2x, and here we have 11. Now dividing throughout by 2, we have 5 over 2, and here we have e raised to 2x, and here we have 11 over 2. So now we have this inequality involving the exponential function, right? So now we have to get rid of this exponential function, and we have to simply find out x. So what we will do, will take the natural log of this inequality, right? So taking natural log throughout, we have that is log of 5 over 2. Here we have log of e raised to 2x, and here we have log of 11 over 2. So this is the natural log of 5 over 2, and here this term, that is natural log of e raised to 2x, is equal to 2x. Natural log of e is 1. So we have 2x times 1, that is simply 2x. So here we have 2x, and here we have natural log of 11 over 2. So now dividing throughout this inequality by this factor 2. So we have half natural log of 5 over 2, and here we have simply x, and here we have half natural log of 11 over 2, right? So we can see that the values of x lies between these two numbers, including the numbers, because here we have the equality, right? So we can write half natural log of 5 by 2 as natural log of square root of 5 over 2, and here we have x, and here we can write natural log of square root of 11 over 2, right? So from this inequality we can conclude that x belongs to the interval, that is natural log of square root of 5 over 2 comma a natural log of square root of 11 over 2, right? So these are the required values of x for which the function f of x, which lies between 2 and 5, including 2 and 5. So the required range of all the values of x are given by this interval, right? So viewers, this is how by making use of the fundamental theorem of integral calculus, that is by differentiating this equation both sides with respect to x, we can find out the required values of x in this given problem. Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals. And here we are going to discuss this problem in which we are given a function f which is from open interval 0 comma infinity to the set of real numbers, and we have a function g of x that is equal to integral 0 to x f of t dt, and further we are given that g of x square is equal to x square times 1 plus x. Then we have to find out the value of f of 9. So now to solve this problem, we have to make use of the fundamental theorem of integral calculus. And fundamental theorem of integral calculus says that if we have a function, say a of x, which is equal to the integral a to x, and we have f of t dt, then the derivative of a of x, that is a prime of x, is equal to f of x, right? Where this function f of x is a continuous function in the interval that is closed interval a comma b, and this point x, it lies between a and b, right? So we are going to use this statement to solve this problem. So here we are given that g of x is equal to the integral 0 to x f of t dt. So now if we differentiate both sides, that is d by dx of g of x, then we have d by dx of the integral 0 to x f of t dt, right? So here we have seen that when we differentiate both sides, that is d by dx of a of x, then we get a prime of x, and here when we find d by dx of the integral from a to x f of t dt, then we get f of x, right? So replacing this t by x. Okay, so here we have d by dx of g of x, so the g prime of x is equal to f of x, right? So we have g prime of x is equal to f of x. Now let us consider this equation, that is g of x square is equal to x square times 1 plus x, which can be written as x square plus x cube. So now differentiating both sides with respect to x, we have d by dx of g of x square, and here we have d by dx of x square plus x cube. So the derivative of g of x square is g prime of x square, and by chain rule the derivative of x square is 2x, and here the derivative of x square is 2x, and here the derivative of x cube is 3x square. So now we have 2x g prime of x square, and here we have 2x plus 3x square. Now taking x common from these two terms, we have x, and here we have 2 plus 3x. Now we can cancel this x with this x, because here x belongs to the interval 0 to infinity, and x is not equal to 0. So we have now 2 times g prime of x square is equal to 2 plus 3x. So g prime of x square is equal to 2 plus 3x divided by 2. So now this is a functional equation, that is g prime of x square is equal to 2 plus 3x over 2. So let us replace x square by some other variable, say y. So we can now write g prime of y, and here we have 2 plus 3x. Now when we are replacing x square by y, it implies that we have to take x is equal to square root of y. So here we have square root of y, and here in the denominator we have 2. So we can now write g prime of y is equal to 1 plus 3 over 2 times square root of y. So again changing the variable from y to x, that is the usual notation. So we have g prime of x is equal to 1 plus 3 over 2 times square root of x. Now g prime of x is equal to f of x. So replacing g prime of x by f of x, we can now write f of x is equal to 1 plus 3 over 2 times square root of x. So this is our function f of x. So we have find out the value of f of x. So now we can easily calculate the value of f of 9. So f of 9 can be obtained by replacing this x by 9. So we have 1 plus 3 over 2 times square root of 9. Now here we can write 1 plus 3 over 2, and square root of 9 can be taken as plus minus 3. So taking the square root of 9 as plus minus 3, and now taking first taking the positive sign, we have f of 9 is equal to 1 plus 3 over 2 times positive 3. So we have 1 plus 9 over 2, that is 2 plus 9 over 2, that is 11 over 2. So f of 9 is equal to 11 over 2 when we have the positive square root, that is plus 3. Now taking the negative square root, so we have f of 9 is equal to 1 plus 3 over 2, and here we have minus 3. So this is 1 minus 9 over 2, that is 2 minus 9 over 2. Here we can write 2 minus 9 over 2. So f of 9 is equal to minus 7 over 2. So here we have obtained two values of f of 9. The first one is 11 over 2 and the second one is minus 7 over 2. So 11 over 2 is corresponding to the positive square root, that is plus 3, and minus 7 over 2 is corresponding to the negative square root, that is minus 3. Hello viewers, in today's session we are going to discuss another important problem from definite integrals, and in this session we are going to discuss this problem in which we are given a function f which is from the open interval 0 comma infinity to the set of real numbers such that integral 0 to x square f of t dt is equal to 2x square minus 3x plus 1, and then we have to find the value of f of 4, right? So here we are going to use the concept of Leibniz integral rule, which is differentiation under the integral sign, and we'll see how easily we can find out the value of f of 4. So let us first quickly see the Leibniz integral rule. Suppose we have an integral where the lower limit and the upper limit are functions of x. Suppose here we have u of x, here we have v of x, and here we have a function f of t dt, right? And if we differentiate this function or this integral, that is from u of x to v of x f of t dt with respect to x, then Leibniz rule says that the derivative of this integral with respect to x is given by f of v of x. First we'll replace this t by v of x, and then we differentiate this function, that is v of x with respect to x, right? And then here we have a negative sign, and then we replace this t by u of x, so we have f of u of x, and then we differentiate u of x with respect to x. So this is the Leibniz integral rule, and here we are going to use this rule to solve this problem. So now let us differentiate this given equation both sides with respect to x. So we have d by dx of the integral from 0 to x square f of t dt, and here we have d by dx of 2x square minus 3x plus 1, right? So now if we compare this expression with this one, then here u of x is given by 0 and v of x is given by x square, right? So now this expression is equal to this one where u of x is 0 and v of x is x square. So let us write here the values of u of x and v of x. So this side is now equal to f of v of x. V of x is x square, and then the derivative of v of x, that is d by dx of x square, minus here we have f of u of x. U of x is 0, and here the derivative of u of x, because u of x is equal to 0, so here the derivative of 0 is 0, and here we have the derivative of x square as 2x, so this term is 4x, and here the derivative of x is 1, so here we have simply 3, and the derivative of 1 is 0 being a constant. So here this term reduces to 0, so we are left with only f of x square. Here the derivative of x square is 2x, and here we have 4x minus 3. So now f of x square is given by 4x minus 3 over 2x, right? So this is a functional equation, and here we can see that x appears in the denominator, and here the domain of the function is the open interval, that is 0 to infinity. So here obviously x is not equal to 0. So now let us replace this x square with other variables, say y. So when we replace x square by y, it implies that we are replacing x by square root of y. So now this functional equation takes the form f of y, that is equal to 4 times square root of y minus 3 divided by 2 times square root of y. So here we have replaced x by square root of y and x square by y. Now again replacing the variable y by x in the usual notation. So we have f of x is equal to 4 times square root of x minus 3 divided by 2 times square root of x. So now separating the terms, we can also write this expression as 2 minus 3 over 2 times square root of x. So our function f of x is equal to 2 minus 3 over 2 times square root of x. So now we have to find out the value of f of 4. So let us replace x by 4. So we have f of 4 is equal to 2 minus 3 over 2 times square root of 4. So we can now write 2 minus 3 over 2 times square root of 4 is plus minus 2. Now first we can take the positive square root. So f of 4 is equal to 2 minus 3 over 2 times plus 2, that is equal to 2 minus 3 over 4, that is 8 minus 3 over 4, that is 5 over 4. And when we take the negative square root here, then f of 4 is 2 minus 3 over 2 times minus 2. So here we have 3, that is 2 minus here this negative and this negative becomes positive, so we have 3 over 4. So this is now 8 plus 3 over 4, that is 11 over 4. So when x is equal to 4, then we have two values of f of 4, that is 5 by 4 corresponding to the positive square root of 4, and f of 4 is 11 over 4 corresponding to the negative square root of 4.